name is Chris Kernizak, teach at Swampscott High School. I'm a physics teacher there, here for the summer with the RET program, and the project we're working on is magnetic array imaging. Before I get into that, I'm just going to discuss some of the basic ideas behind the Hall effect. The Hall effect takes place when you use a semiconductor to conduct electricity. Basic Hall effect probe or sensor is incredibly small. I don't know if you'll be able to zoom in on that. Can you see it?
There's no zoom.
Or can you even see it? It's on my fingertip right now. It's a very tiny little sensor. And I can just draw a picture of it on the board. But this sensor looks something like this, called the Hall effect sensor. It has 3 leads that come out of it. In this region right here is a semiconducting material. What you do is take one of these leads. One will be red, which is your hot lead for coming from a power source, and the other will be your ground wire. So if you had a power source, you would connect your red to one of these and your ground to the other one. This is ground. Once you actually connect these to your Hall effect sensor, you have electricity that flows through. And electricity starts to flow up this, and then it turns around and comes down out the ground side. If we were looking very closely at that in this diagram, this is a zoomed picture of this semiconducting material. Let's assume that the current is coming in from this side. Normally current is labeled by I. I stands for current. And the direction is showing that the current is flowing in this direction. This would be electrons flowing in this direction. What happens is when you place this Hall effect sensor in the position or in the vicinity of a magnet or a magnetic field, something interesting happens. Prior to putting the magnet there, nothing interesting happens. Your current just flows in a very straight line and then turns around and heads out. Fair enough. But as soon as you take a magnet, let's say this was a big bar magnet here, and if I could also draw what a magnet would look like. Let's say this is my magnet. The fields look like this. They're all loops, like this, looped magnetic fields coming out of a bar magnet. One side is considered north, and the other side is considered south. Very close to one of the poles, let's say I looked very closely at the north pole, the field is approximately coming straight out, even though it does loop around and come back like this. So you just imagine this as a big magnet with fields coming straight out. And when I place the north, let's say this was the north pole of my magnet, near here, while current is flowing through, what happens is the flow of the electricity, rather than being straight, ends up bending like this to one side. The reason you get this bending is because there's a magnetic force. And that magnetic force acting on the electrons as they pass through is called the Lorentz force. The Lorentz force happens whenever there's motion between moving electrons and a stationary magnet. That would be relative motion between the magnetic field or the magnet and the charges. Or you could have stationary charges and move your magnet. But as long as there's motion between the two, the electrons and the magnetic field, you get a force. And the force always ends up being perpendicular to the direction the charge is traveling. In this example, the charge is traveling this way, and so it receives a force. We normally label that F with a B. B stands for magnetic force here. And the direction of the force that the electrons experience is this way. The field is going into the board. If I was holding my magnet here, the field is going into the board. The flow of the electrons is this way. That was my I going this way, and the magnetic force is this way. You also would get, if there was some positive charges in here, because remember the flow of negative flow of electrons is negative. There are negative charges. They're going to get a force that's in one direction. If there's positive charges in here, they actually get a force in the opposite direction. So if you had a positive and a negative charge traveling in the same direction, and you put a magnet near them, the negative charge, meaning maybe upward, and the positive charge would have a force on it downward. Both those forces are from the magnet, the magnetic force. And so you end up having positive charge that builds up here on the bottom, and then you have negative charge that builds up, running out of marker there, you get negative charge that builds up on the top. And it's almost like a spreading effect. By placing the magnet there, the charge spreads out. If you remove the magnet, you just get current flowing in straight through the middle. And the idea is that this actually is what generates a voltage. By placing similar charge on a surface, you build up a voltage. And here we have a similar negative charge on one surface and similar positive charge on the other. And so therefore you get a voltage. This whole effect is called the Hall effect, and it's based on the Lorentz force, that when charge moves through a semiconductor in the presence of a magnetic field, which would often just be a magnet you could stick there, you get this spreading effect. So if you if you had a voltmeter, which I can show here.
Go ahead.
This here is a voltmeter, and it has a black and a red connection, or a ground and a red connection. If you were to take this and actually connect one side to one of the sides of the semiconductor where the charge is building up, and you would connect the other to the other, and turn this on to a DC reading, you would actually measure a voltage. So the interesting thing is that when I put the magnet very close to this sensor while the electricity is flowing through it, they really spread apart a lot, and you would get a lot of charge built up here and a lot of charge built up there, and that would correspond to a large voltage on the voltmeter. If I moved my magnet away, the magnetic field is a little weaker because it's further away from the sensor, and therefore you'd get less pileup of positive charge here and less pileup of negative charge there, and you'd have less voltage. And so there's this correspondence between how strong the magnetic field is at the position of the sensor and the Hall voltage, which is the voltage that you're measuring with your voltmeter. And so in that way, we'll be able to use the Hall effect sensor as a magnetic field sensor.